Hey, welcome back. So this is now 10.3. We're going to start moving into calculus. So not much of what we've done so far is actually been calculus type stuff. We want to include the derivative and then the integral, so we'll start doing that now in 10.3. So the first thing we'll get is the derivative formula. And the first derivative is pretty simple. You basically just take the ratio of the derivative of the formula for y and put it all over the derivative for the formula for x. Okay, so basically, given our parametric equations, so let's say x is f of t and y equals g of t, we have then the derivative of y with respect to x, the derivative we all know and love, is going to be g prime of t all over f prime of t. The bummer part is that the second derivative is not going to be so easy, sadly enough. So how do I get my paws on that? I'm going to take the derivative of the first derivative with respect to t and put that all over the derivative of x with respect to t. And you can kind of unravel that via the chain rule if you want to get ambitious about it. But I in my opinion, in my work, I've not really found a nice, clever way to kind of remember that. Maybe somebody has, I haven't. Okay, so anyways, let's look at some problems. Number 3 is where we'll start, so a pretty simple one. And you should be able to kind of, at least in these examples, produce the normal derivative. Okay, so what do I mean by that? Well, you can, eliminate the parameter here. So I could say t must be x over 5, and then put that into the y formula. So y is 7 times x over 5 minus 3. So y is 7/5 x minus 3. So I'm saying that the derivative with respect to x is going to be 7/5, basically the slope. And then the second derivative with respect to x is 0. And t, the parameter, for us, we want to evaluate the derivative, the first and second derivative at t equals 4. Anyways, all I'm doing is trying to demystify these equations. They will give you the same exact thing that you're looking for in the xy plane, and namely the slope of the tangent line to the curve. Okay? It's just we're going to be able to get a little bit more coolness out of this, and that we can find vertical tangent lines now too. So anyways, let's use now the formulas, right? So dy over dx is going to be the derivative of y with respect to t. So the derivative of 7t minus 3 is just 7, divided by the derivative of x with respect to t, and that's just 5, right? And of course, we get what we expected to get just using plain old Calc 1. Let's go to the second derivative. So this time, it's the derivative of the first derivative with respect to t all over the derivative of x with respect to t. Okay, so the derivative of the first derivative, this constant with respect to t, is just 0. And then all over the derivative of x with respect to t is 5. So this will be 0. Okay. In the homework, they ask some silly questions. They want to know then what's the slope at t equals 4. Well, at t equals whatever, the slope is always going to be 7/5. Okay, so for any t, and in particular for t equals 4, the slope is 7/5. Okay, great. On the other hand, then, the second derivative tells you concavity. And this is a little weird because we have 0. So what is 0? That's nothing. It doesn't have concavity there. I believe that'll be, that's the inflection point, right? That's where you take the second derivative, set it equal to 0. It's kind of like a critical number, but this is where inflection points potentially happen. If you think about a straight line, well, I mean, you think about it, it's not even an inflection point, right? It's just there's nothing there. A straight line looks like this. There's no concavity. What's the concavity of a straight line? Well, it doesn't have one. So what the heck do I put for my answer for concavity? You know, it's going to ask for it. Well, you're just going to write does not exist. And then it has a follow-up question. I believe you just say neither. Okay. I'm sorry that that's weird, but you're dealing with a computer, and nobody wants to grade anymore, so everybody wants to do homework online. Okay, so neither is the second answer that they want to know. So basically they're asking, is it concave up or is it concave down? So first they want to know the value of the concavity. Because it's 0, you'll say not 0, but you'll say it does not exist. And then the follow-up question, is it concave up or concave down? You'll just say neither. Okay? Okay, I hope that helps. Number 4, this one's a little bit more complicated, but you're not going to have those weird issues like what is concavity of 0? 4t minus 4, and then t equals 1. Okay, so first let's get the derivatives. So you put the derivative of y, which will just be 4, all over the derivative of x. Let's rewrite x to be t to the 1/2. So its derivative is 1/2 t to the negative 1/2, which will be 8 square root t when all is said and done. And then we want to evaluate. To notate evaluations, what we usually do is, it's a little bit like the integral notation, but not really. It's just a vertical line, and then at the bottom, write t equals 1. That will allow your reader to know that you're substituting in this value for t, and in our case that will be 8 square root 1. That will be 8, and that's the slope. It'll ask for the slope, you'll type in 8. All right, second derivative. Okay, so the second derivative, it's not just a matter of taking the derivative of the first derivative, right? It's not going to be 8 times, it's not going to be 4 over square root t, right? No. What you do in the numerator is put the first derivative in our traditional idea of, and I'm putting dt in the denominators even though I meant to put dx. I want dx, not dt. Okay, so in the numerator you put the derivative of this thing. That will be 8 times 1/2 t to the negative 1/2. And then the denominator, you put the derivative of x with respect to t, and that's this thing right here. Okay, so see what I mean? You can't just take the derivative of the first derivative. It don't pan out. All right, so here the t and the negative 1/2s cancel, the 1/2s cancel, so you just get 8. So the concavity is always the same. This must have been some sort of like a parabola or something at the end of the day. Evaluating anywhere is just going to give you 8, but in this case, yeah, we'll write it out. And that's going to be your concavity. Concavity is 8. And then the follow-up question, what is it concave up or concave down? If it's positive, it's concave up. If it's negative, it's concave down. So in this case, it's concave up. Okay, great. From there, we're hashing out all the old Calc 1 stuff. So now they want you to find the equation of a tangent line to a curve. In particular, the curve here is x equals t squared minus 4, and then y equals t squared minus 2t, and they want the tangent to the curve at the point 0, 0. This is x and y. We need to then find the t value. Okay. All right, so the first thing is just finding the stupid t value, because it's not just going to be 0, right? So how do I figure out the t value? You're going to have kind of a system of equations. So you're going to take the x equation. You want x to equal 0, and then you're going to have to solve for the t value. That will just tell you where the x equation is equal to 0. Doesn't say anything about the y equation, right? You need simultaneous zeros on both ends in both equations, right? So you have t squared is 4. So t is potentially plus or minus square root of 4, which is 2. So that's where x is 0. And then we find where y is 0. if y is at 0 at plus or minus 2, we're going to have two tangent curves. But let's see. So I replace y with 0. Then I can factor. And then it looks like t is 0 or t is 2. So the only place where they're both going to be 0 is when t is plus 2, right? At 0, certainly the y is 0, but then the x is not 0. At negative 2, the x is 0, but then the y is not 0. Okay, so you see the issue? You got to make sure they're both equal to 0. Okay, great. Secondly, then, in order to get the equation of a tangent line, we need what? We need two things. We need a point, which we already have, and then we need a slope. And then we put it into our famous point-slope form. Okay, so the slope. So how do I get the slope? It's the derivative. And in this parametric setting, I take the derivative of y with respect to t. That'll be 2t minus 2 all over the derivative of x with respect to t, which is just 2t. And I know my t value is 2, so I need to evaluate this thing at that value. And so that will be 4 minus 2 all over 4, which is 2 over 4, which is 1/2. Okay, great. So from there, I can form the equation of a line. So I'll go y minus, my point is 0, 0. So 0 equals 1/2 times x minus 0. And then I have y equals 1/2 x. And you probably typed that whole thing in there for your answer. Okay, okay, great. We can find vertical tangent lines now. So before, whenever we had a vertical tangent line, we would just have to say, well, the derivative does not exist. Okay? I think they may have even gone far enough to define that as the vertical tangent. It happens when the limit of the difference quotient goes to infinity or negative infinity. Okay? They may have defined that in the book. I don't remember, but here we're going to be going after those points. Okay, so section 2, we are looking for horizontal, not only horizontal, because that was a big deal in Calc 1, right? So if you look where the horizontal tangents are, that tells you how to optimize your function. That was the whole, reason behind why you were going after critical numbers. You want to optimize a function. You know that the optimal points happen where the tangent lines are vertical, right? So there's a max, there's a min. So you get the derivative, set it equal to 0, and then you could kind of speculate as to where those maxes and mins were. All right, so great. Now, not only are we able to get our hands on these horizontal cats, but we're also going to be starting to go after the vertical guys as well, right? So how do I do that? Well, it's like critical points, but now not just the x positions. Okay, so you're going to have, for the horizontal, you're going to take the y formula and set it equal to 0. Okay, because you can think of slope is kind of like change in y over change in x. So these positions would happen when change in x is equal to 0, when that numerator is equal to 0. Then when the denominator is equal to 0, that's when you're going to get your vertical asymptotes. Please note when they're simultaneously equal to 0, that's when you have the non-smooth places. So that's when you have the kinks, and that's kind of trouble. But anyways, for the vertical, you just look for where the derivative of x is equal to 0. And of course, then you want to be careful that they're not both equal to 0. So anyways, let's look at number 7. You have two parametric equations, y equals cosine theta and y equals 2 sine of 2 theta. It's not clear what this object is, okay? It would be hard to eliminate the parameter because I don't have the same, it's not like cosine theta and then sine of theta, right? So that's a bummer. But we could still go after these vertical and horizontal asymptotes. Okay. Okay. So for the horizontal, I'm going to get the derivative of x with respect to, in this case, theta. And so that'll be negative sine of theta. And then I'm going to set that equal to 0 and find the theta values. So there's going to be an infinite number of potentially vertical asymptotes. All right, so set this equal to 0. And then I'm looking for wherever that thing is equal to 0. So sine is equal to 0 where? Well, it's here, first off. And then you can move over to here. So basically, you start at 0, and then you can add in pi. And then you can add in another pi, and it'll be 0. And then you can add in another pi, it'll be 0. And then you could go backwards by pi, it'll be 0. Back again by pi, it'll be 0. In other words, any multiple of pi will do. So this will be equal to 0. The derivative of x will be equal to 0 at any multiple of pi, any integer multiple. That n value, if you're not sure about what the heck that means, it's any negative counting number, 0, and then any positive counting number. Okay, great. Then I go after dy with respect to theta. And again, I have a bit of a trigonometric equation to handle. Divide both sides by 2. And then you're asking, where is 2 theta going to give you values such that the sine of 2 theta is equal to 0? Okay. Whoops. And of course I screwed up the derivative of sine. How could I have screwed that up even? I apologize, folks. I'm sorry. The derivative of 2 sine 2 theta is actually cosine 2 theta times 2. So with the extra factor of 2 in the front, you get 4 cos. I apologize. And then set that thing equal to 0. And then you're looking for where you end up with the inputs, these 2 theta inputs, causing cosine to equal 0. So cosine is equal to 0 at pi over 2, and then you can move over by pi, and you get 3 pi over 2, and then 5 pi over 2, or in the other direction as well, right? So you're starting at pi over 2, and then you can add in multiples of pi. Okay, but if you put that expression as is into cosine of 2 theta, it's not going to work. What you need to do is then divide both sides by 2. So this will be pi over 4 plus pi n over 2. Okay, so you may need to review a bit of trig in order to stomach that. But okay. So, anyways. These guys are never simultaneously going to be equal to 0. Okay, so that's a non-issue. What do we need to do now? We need to figure out exactly what are these points on the graph where you have the tangency. And we don't want the theta values. We already know the theta values. What we want to know are the xy coordinates for these particular theta values. Okay, so what I'll do is just put in some n values and see what happens. So if I put in a 0, or I mean, we can even put in the n with it, and it's not going to make a big deal. It's not going to be a big deal. So you're plugging these values not into the derivative, but into this x equals cosine theta formula back up at the top, this thing. And then you're kind of thinking, what is the cosine of pi n, right? So you can do some experiments. You plug in 0, and when you have that case, okay, so it's, x is that, but then y, I need the y formula as well. So y is 4 cosine of 2 theta. So this would be 4 cosine. Are they both cosine? No, I looked at the derivative. 2 sine of 2 theta. So in this case, it's going to be 2 times pi n. Anyways, for the, think about the unit circle. For cosine of pi n, it's going to be negative when n is odd, right? So when n is 1 or 3, it's going to be, x is going to be -1, right? So when n is odd, and then when n is even, x is going to equal +1. So it'd be like 2 pi or even 0 as we have here. So cosine of 0 is going to be 1. And then we want to do the sort of same analysis with this other guy, right? So, you know, and then if we just had 1 pi, that would be -1. But when n is when n is odd, then y is going to be, well, it's going to be 0 no matter what, right? So 0, and if it's odd or even, just any multiple of pi and to sine is going to be 0. So this will be 0, this will be 0. So ultimately on the graph, if what it's doing is kind of retracing itself as it's being drawn, you're going to have these 2 points, -1, 0 when n is odd, and then 1, 0 when n is even, and these will be, because we are looking where the derivative of x is equal to 0, these guys are going to be your vertical tangents. Okay, then we just do the same business with this other guy. If you want to, you could do some concrete test values, like try pi/4, and what this really is 2 pi/4, right? So then the next one would be plus 2 pi/4 is 3 pi/4, and then 5 pi/4, and then like 7 pi/4. And what you're doing is traveling around the unit circle, and it will affect some of the signs in your answers. So at pi/4, you're in the first quadrant, 3 pi/4 second quadrant, 5 pi/4 is the third quadrant, 7 pi/4 is the fourth quadrant. So again, using our formulas, x equals cosine of pi/4 plus, you know, your 2 pi n/4. Let's not go through the even and oddness, because it's going to be a bit of a nightmare, because it's not really an even odd thing, right? You're putting in you're putting stuff in and then you're adding it, so it's going to be maybe a little more complicated. So let's just look at these four locations. After you get through these locations, it's just going to repeat itself in the unit circle. So you really need to only look at these. Like if I go up to 9 pi/4, that's going to be equivalent to 1 pi/4. If I go back to negative pi/4, that's the same thing you would get if you plugged in 7 pi/4. Okay, so I can kind of avoid having to do, oh, is this even or odd type analysis, just by that observation. Okay. So anyways, I got cosine of theta for x, and then y, I said 2 sine 2 theta. Okay, great. So cosine of pi/4 is √2/2. Then sine, it will be 2 times pi/4, which is pi/2, so that would just be 2. Okay, 3 pi/4, so now cosine is negative, so it would be -√2/2. And then the y value is going to end up being 3 pi/2. Sine of 3 pi/2 is negative, so this will be -2. 5 pi/4, cosine still negative. Oops, sine is positive in that quadrant, so that would have been, sorry, 3 pi/, sine of, but it changed, right, because there's that multiple of 2. So it's actually, yeah, it's still -2. All right. 5 pi/4, sine of 5 pi/2 is what that is going to amount to. So maybe there isn't. I don't know. All right. So anyways, 5 pi/4, 1, 2, but when you put it in, it's 5 pi/2. So 1 pi/2, 2 pi/2, 3, 4, 5. So it's +1. So you get 2. 7 pi/4 cosine will be positive now, so √2/2, and then y, the output of y is going to be 7 pi/2, so 5, 6, 7. That'll go down to negative. You literally get every possible combination of positives and negatives for your horizontal tangent. So your horizontal tangent would be root 2 over 2, comma 2, negative root 2 over 2, comma negative 2, negative root 2 over 2, comma 2, and then positive root 2 over 2, comma negative 2, and then they'll want you to order them according to their little program in WebAssign, whatever they do. Okay, so there's that. I think my rationale for why I only had to look at those 4 values is a little suspect, so you may want to think through that a little bit. But anyways, the last topic here then introduces integration. So we have arc length. We've seen the arc length formula before, and if you remember it, it has this kind of distance formula look to it. So it's a sum of a bunch of distances, and the way we got our hands on that distance formula was to it was kind of a matter of distance formula and plus the mean value theorem. So we were able to eventually do some factorization and then replace dy over dx with via the mean value theorem. So f prime of c is equal to the f of b minus f of a over a minus b, and then we could use that f prime in place of this position. Oh, okay, but anyways, now because we kind of have derivatives for each individual guy, it looks a lot more like the distance formula. Okay, so it's going to be, basically the distance formula is the square root of x2 minus x1 squared. So that's, you think of x2 minus x1 like change in x. Okay, so it's x prime of t squared and then plus change in y, which is y prime of t squared dt. And now everything's in terms of the parameter t. Okay, let's try number 8 because I thought 8 was a bit annoying, and then I'll give you the quiz and we'll be done with it. So x equals e to the negative t cosine of t, y equals e to the negative t sine of t, and then what's going to become a trouble, sort of a problem in later sections is this parameter. The problem is that when we draw these like highly symmetric objects like circles, or even we'll look at rose petals and stuff like that, they will have this property where they'll kind of retrace themselves. Okay, and of course if you saw that curve.com thing that we went to, those curves retrace themselves over time. And if you're integrating and you don't know where to integrate to, you may accidentally over-integrate. So you'll basically trace out the curve more than once and you'll have too much. The arc length value will be too much. So we'll have to be more careful, and that will, in order to pull that off, we'll have to do these things by hand. We'll have to be able to graph them by hand. So the calculator is not going to go and tell you, ooh, you have to graph from here to here. Okay. You may be able to kind of get away with like knowing about where it's smooth or where it crosses the origin. You could kind of use that. There's all kinds of symmetry stuff that you used in trig if you studied polar curves in trig. But honestly, you usually forget all that stuff, right? So anyways, we'll have to draw these things by hand is where we're headed. Anyways, let's get the derivatives. So I got to do product rules. Leave e to the negative t alone, and then you get negative sine t, and then plus the derivative e to the negative t is e to the negative t times negative 1. Leave cosine alone. Clean it up a bit. Okay, do the same thing with y prime. So here I'll have then e to the negative t cosine t plus, and again, the derivative e to the negative t is e to the negative t times, from the chain rule, negative 1. Leave sine t alone. And then this character is e to the negative t cosine t minus e to the negative t sine t. And then to put it in our formula, we have to square both of those, right? Oh, how annoying. So anyways, here we go. sine is the integral, and then they were nice enough to tell us the limits on the integral from 0 to pi over 2. Like I said, that's going to be an issue later. And then we have the square root of some huge, monstrous bit of information. We could make maybe our life a little easier by factoring out a negative e to the negative t from the first one. And then on the second guy, factor out e to the negative t. So when we square it, squaring a product is the same as squaring each individual term. So I can square negative e to the negative t. That will just be positive e to the negative 2t, and then FOIL out this thing, right? So that would be then sine squared t plus 2 sine t cosine t plus cosine squared t, and then plus this next guy, squaring e to the negative t is e to the negative 2t. And then I can FOIL out the cosine t minus sine t part. So it would be cosine squared t minus 2 sine t cosine t, and then plus sine squared t dt. And then you can factor out the e to the negative 2t from both terms, and you get e to the negative 2t times, all right, this junk and this junk. Okay. This plus this is equal to 1, right? So I'm going to have 1 plus 2 sine t cosine t. And then again, this plus this is equal to 1. So I'll have 1 minus 2 sine t cosine t. And then lo and behold, when I add those two together, I'll just have 2. Punchline, right? Okay, so what? Well, now I can, the square root of a product is the product of the square roots. So I have square root 2 times square root of e to the negative 2t. Let's rewrite that as e to the negative 2t to the 1/2. You can factor out the square root of 2. Then you get e to the negative t dt. And then you can do a u sub. And so I'll have root 2 integral e to the u times negative du. Take out the negatives, so I get root 2. The integral of e to the u is just e to the u. Got to remind myself to evaluate. Back subbing first, e to negative t, evaluated from 0 to pi over 2. So that'd be negative root 2, e to the negative pi over 2 minus, you have the minus, be careful. Negative root 2 times e to the 0. So this will end up being negative root 2 e to the negative pi over 2 plus root 2. E to the 0 is 1. Okie dokie. Okay, so for the quiz this time, find the arc length of half the circle given by the parametric equations x equals cosine t, and then y equals sine t. So half the circle means you're integrating from t equals 0 to t equals pi, right? So if you were to graph that thing out, you eliminate the parameter, you get cosine squared plus y sine squared is equal to 1. That'd be x squared plus y squared is equal to 1. But the parameter going from 0 to pi is going to go from here and then have that orientation right to there. So the hope I don't embarrass myself, the circumference of a circle is 2 pi r. So that's the circumference. Half the circumference should be basically your answer. So your answer should be pi r. And what's the radius here? Well, your answer should be pi. So I need you, though, to use the formula for arc length, making it more obvious. The formula for arc length is this formula. For those of you who like the helicopter in and just watch quiz, there you go. That'll prevent me from having to argue with you over your answer. Okay. Anyways, that's the quiz. Thank you for watching, and I'll see you next time.